So, taking these two ideas, the idea of induction, about this coil and this magnet traveling through there, generating a push on the electrons in one direction, and then generating a push on the other direction as the magnetic field goes through it. And this idea of flux, we can come up with an idea in which we can generate electricity. Now, the thing about just exposing it to a magnetic field, like we did with this example, coil, is that eventually well, not eventually, very quickly, the system will achieve equilibrium. So if you continue to expose this field to a magnet, or that coil to a magnetic field, that eventually the electrons will build up at a point and you won't get any motion of charge. It achieves an equilibrium. For every charge that you're moving, it's pushing on another electron and pushing on another electron. And eventually you can't generate enough push to get those electrons to move. Okay? So simply exposing a coil to a magnetic field won't generate an electric field. An electric current, sorry. The truth of the matter is, the only way that we can generate an electric field, at least using magnetic fields and coils, is if we alter the flux. Okay? If you remember, flux was B times A, basically. Magnetic field times the cross-sectional area in which that magnetic field is exposed to. In the case of this wire, this was the area, we had a magnetic field, okay, generating flux. Now, it turns out that only a changing flux, only a flux that's changing will generate electricity. Okay? So, either we can develop a way in which we can change the strength of a magnetic field, which can be done. I mean, we do that with electromagnets all the time. Or a way in which we can change the cross-sectional area, we can generate ourselves an electric field. Okay? So, the change in flux produces an electric field. So, what we like to say is, equation-wise, that the change in flux, or the change in time in which that flux is happening, so basically the rate in which my flux is changing, is equal to my EMF. Okay? And EMF is a potential difference. It's a voltage. But it's a particular type of voltage. This is the maximum possible voltage. Now, if you're looking at a battery, you're not looking at the EMF of that battery. You're looking at the voltage of that battery. Inside that battery, there's some sort of internal resistance. That internal resistance reduces your EMF. So some sort of internal resistance reduces your EMF to a voltage. And that voltage is the printed value on your battery. Okay? So that's the difference. EMF is the maximum possible voltage. Cool? We're talking about internal resistance, and then we're talking about the voltage that's printed on your battery. Okay? Now, so this change in this EMF over the change in time, the rate in which the flux is changing, produces that voltage. So if it's a very fast changing flux, you're looking at a very big EMF. The other thing that can affect that amount of voltage is coils. Okay? If I have multiple coils instead of just one, each one of those coils is experiencing the magnetic field. Each one of them has current or charge that's being moved by that magnetic field. So increasing the coil increases the potential for coils to move, for a charge to move. So more coils, more EMF. Okay? And then we throw a negative sign in there just because of orientation. Cool? So when we talk about induction, this is what we're talking about. You can produce a voltage by changing a magnetic field, or changing cross-sectional area, as a matter of fact. that is induction.